Hi, AP Chem students. In this video, we will try to determine whether a salt is neutral, acidic, or basic when dissolved in water. And then we will calculate the pH of these salt solutions given the initial concentration. So salts are ionic compounds. They're soluble ionic compounds that form from the reaction of an acid and a base. So here, when we have ions in the salts are made of a positive and a negative ion, cations and anions. These ions reacting with water are what cause a change in the pH. So in this case, for example, we have the acetate ion. It will react with water and form acetic acid and some OH minus. That causes base to be formed. So this ion is a basic ion. So we can write hydrolysis reactions for any sort of ion. So for example, this bromate ion can undergo hydrolysis with water. And hydrolysis is just a fancy way of saying an acid-base reaction. This is written exactly the same way as we've been writing these acid-base reactions. So the proton is transferred to the bromate ion, and we get some OH minus. So again, this bromate ion is a basic ion. So let's see where these ions come from. So when we take a look at the anions of salts, the anions of salts are the conjugate bases of weak or strong acids. Now, if we have the conjugate base of a weak acid, we are going to get a weak base. So for example, our acetate again, right? Acetic acid is a weak acid. Its conjugate base is a weak base, so that can react with water to form some OH minus. On the other hand, the conjugate base of a strong acid, such as our strong acids here, HCl, HBr, HI, HClO3, HClO4. We also have HNO3 and H2SO4. These are neutral, right? All of the conjugates of these strong acids are neutral. So Cl minus, Br minus, I minus, etc. These will not regain the proton, right? That's why they're called strong acids, because they stay dissociated, they stay ionized, and they do not take the proton back. So these conjugate bases, I like to say that they are pathetic as acids. They are pathetic ions that can't react with water. Some conjugates are amphoteric. Okay, here are two amphoteric ions. What does amphoteric mean? It means it can be an acid or base. It can act as an acid or a base. And so we could write two hydrolysis reactions for HCO3 minus. We could have it act as an acid where it gives up a proton to water. So it could transfer a proton to water, forming hydronium plus CO3 2 minus. That should be a HCO3 minus here. Or it could act as a base where it takes a proton from water. Here it's going to form H2CO3, carbonic acid, plus OH minus. So some ions are amphoteric and can accept a proton or donate a proton. Now, if we look at the cation, cations of salts are conjugate acids. So the conjugate acid of a weak base is a weak acid. So any weak base, the conjugate acid of that weak base, such as NH3, this is the conjugate acid of NH3, which is a weak base. So therefore, this is a weak acid. and forms some H3O plus in water. On the other hand, cations of strong bases, okay, are all our group 1s, remember? So Na plus, Li plus, K plus, rubidium plus, cesium. These ions are going to be neutral ions. They are pathetic, okay, at reacting with water. They are too pathetic to react with water. All cations except for those from strong bases are going to be weak acids. So any other cation, such as this copper ion, iron ion, aluminum ion, anything that is not one of these is going to act as a weak acid in water. So here is the basic guideline for the 3 types of salts. So neutral salts come from strong acid, strong base, okay? Strong for the cation and the anion. Basic salts, the cation is from a strong base. The anion is from a conjugate, is a conjugate base of a weak acid. The acidic salts, the cation will be the conjugate acid of a weak base, and the anion will be from a strong acid. So you can see these examples here of different acidic salts, basic salts, and neutral salts. Okay, so let's summarize the 3 types of salts here. Let's make 3 sections here. Start off with neutral salts. Neutral salts, both the cation and the anion are from strong bases and from strong acids. Okay, so strong for a neutral salt. So you can see how important it is to know which acids and bases are your strong acids and which are strong bases, because, right, if you don't have these memorized, you're going to have to go look them up or take a guess. Instead, right, just memorize them. Then immediately when you see these cations from strong bases, anions from strong acids, you'll immediately recognize them as neutral salts. Okay, and as a reminder, here are all our strong cations. Okay, the cations from our strong bases. We also have calcium ion, strontium ion, and barium ion. Okay, the anions of strong acids, those are going to be Cl minus, Br minus, I minus, nitrate, okay, chlorate, perchlorate, and we need one more, sulfuric. Okay, so those anions, okay, will be neutral anions. All right, so let's go to acidic. So the cation, okay, is going to come from a conjugate acid of a weak base. Remember, the conjugate of a weak base is a weak acid. So here, any weak base's conjugate acid can be the cation and will form an acidic salt. Basically, that's the only part that needs to be acidic. This anion will come from a strong acid. Okay, so it'll be one of these ions over here. If we have a basic salt, then our cation, okay, comes from a strong base. Okay, it's one of these cations here. The anion is the conjugate base of a weak acid, right? The conjugate of a weak acid is going to be a weak base and go into hydrolysis with water. All right, so that's our basic summary, and we need to make sure we know what the strong acids are, what the strong bases are, in order to be able to identify these salts. So we did this exercise just to make sure we understand how to break up the parts here. So this is a soluble salt. We can break it up into 2 ions, barium 2 plus 2 acetate ions. Okay, the cation is going to be barium, and it is from a strong base. The anion is C2H3O2-, and it's from a weak acid. Okay, it's the conjugate base of a weak acid. So this is going to be neutral. Okay, that's that one. I should not point at the strong base, but the barium ion will be neutral. And this acetate ion is the conjugate base of a weak acid. So it's going to undergo hydrolysis. The barium's too pathetic to react with water. It's from a strong base. But this acetate is a weak base, and it can undergo hydrolysis and form the weak acid back and form some OH- as well. So when we have an increase in the OH- concentration, okay, the pH is going to go up, and therefore this, okay, so barium acetate is a basic salt. Now, there are some cases where, what if you have a weak acid ion and a weak base ion? What if both ions come from something weak? Now you have the conjugate of a weak thing with a conjugate of another thing, and both of them could affect the pH. So in the case of NH4F, ammonium fluoride, right, the ammonium could undergo hydrolysis with water, and the F- can react with water. Both of these can produce H3O plus and OH-. So here we need to compare these two equilibrium constants. And the equilibrium constant that is greater is going to determine whether the solution will be acidic or basic. So we can see that this is larger, right? Ka is larger than Kb, so a solution of ammonium fluoride will be acidic when we add it to pure water. The same thing comes up with amphoteric anions. So again, here we would have to compare the Kas and the Kbs of these reactions. Okay, the reaction of HCO3 as an acid and HCO3 as a base, and then compare the Ks for those two reactions, and then whichever one is greater will affect the pH more and will result in whichever, either the acidic or the basic solution. And we'll look at a couple examples tomorrow. All right, so then I asked people to make predictions for these salts. So here I'll just kind of underline, let's see, the ions. Any neutral ions, I will just underline in green. So that's neutral. That comes from a strong acid or base. Just going to go along here and underline all my strongs. Okay, so all of these ions are strong, so they will not affect the pH. But aluminum, okay, is not one of the strong base ions, so it will be acidic. I'll underline any ions that are acidic. NH4 plus is the conjugate acid of a weak base. Okay, and then our basic ions are the anions. So that is not from a strong acid, so that's going to be basic. This is not from a strong acid, so that's going to be basic, and same with the PO43-. So we would expect, based on this, that this is going to be acidic. Aluminum chloride will be acidic. This will be, because of the CO3 2-, we'll have a basic ion. This is acidic. This is basic. And the last one is also basic. All right, and in class, we would usually add these salts ourselves and test the pH. Okay, but instead here, we're going to write out some reactions first, and then there was a video, which I'm going to link in here, that you can watch, and you can see the results of putting these salts into neutral water. For the reactions, we're going to have Al3+, okay, is going to react with 6 waters and form aluminum hydroxide here plus 3 H2Os. Sorry, H3O plus, 3 hydroniums. So the aluminum is a positive ion. It attracts the oxygen and pulls electron density away from the bond between oxygen and hydrogen and causes those water molecules to be more acidic, causing the formation of acid here. So for CO3 2-, it will act as a base and react with water in this way. All right, then our next ion that causes this solution to be acidic is our ammonium. And so it undergoes hydrolysis and forms hydronium plus ammonia. Our next ion is HCO3-. This is bicarbonate. Now notice bicarbonate is amphoteric. It can act as an acid or a base. So in the first case, I'll write it as an acid. So as an acid, it can donate its proton and form H3O plus CO3 2-, or it could act as a base and gain a proton. So it will become carbonic acid plus OH-. And since the overall salt, okay, if we did not know in advance that it was basic, we'd have to compare the Ka to the Kb of these things. But since we know that it's basic, we know that this Kb must be greater than Ka here. So it results in a basic solution. Finally, the sodium phosphate is basic. Our PO4, our phosphate ion, can accept a proton and form some OH- ion, and so that causes our pH to go up. So now, how do we actually, once we make these predictions, we want to be able to actually calculate the pH of these salt solutions. So this is just like any equilibrium problem. We need to write down a reaction. We need to set up a rice table, and then we can calculate the pH by finding either the OH- concentration or the H3O plus concentration. So let's start off by looking at this problem. It says calculate the pH of a 0.1 molar ammonium chloride solution. My ammonium chloride consists of 2 ions. Consists of ammonium plus Cl-. Cl- is pathetic. Okay, can't do anything with water. It's the conjugate of a strong acid. But here, our NH4 plus is a conjugate acid of a weak base. It's going to be acidic. So our reaction is going to be the hydrolysis reaction between ammonium plus water to form ammonia plus H3O plus. Okay, so there's our reaction. All right, so we're going to write down here, this is going to be a Ka, right? Because this is acting as an acid. So we have NH3 times H3O plus over NH4 plus. All right, so our initial concentration is 0.1. Just like before, just set up the rice table exactly the way that we've been doing it. And we end up with 0.1 minus x, then x and x here. All right, so then, right, when I put my values in here, I've got x and 0.1 minus x. But what about this, Ka? I've got the Kb value for ammonia, okay? What we need is the Ka for the conjugate acid of ammonia. So we need to calculate this. Our Ka, and that's where our Ka-Kb relationship comes up, right? Ka times Kb equals 1 times 10 to the minus 14. So we can solve for Ka by using our Kb value, 1.8 times 10 to the minus 5. And we get 5.6 times 10 to the minus 10. So this is the value that we need to stick in for Ka. Okay, so be careful, right? This is from the viewpoint of the conjugate acid reacting with water. So 5.6 times 10 to the minus 10 equals x squared over 0.1 minus x. We can certainly neglect x here and solve for x. So in this case, x would equal 2.4 times 10 to the minus 5. So our pH will be the minus log, and remember that that's equal to the H3O plus concentration. So our pH equals minus log of 2.4 times 10 to the minus 5. And that would be a pH of 4.63 for this solution. And as expected, it is an acid pH. Here's another example. You can try this one on your own. So pause the video and I will provide the answer. So for practice problem number 2, you do have to look up the Ka of nitrous acid in order to do this problem. So the Ka of nitrous acid is 4.5 times 10 to the minus 4. And the pH that you get would be 8.17 is the answer. For practice problem number 3, this is slightly different, where you need to figure out the number of moles required to get a pH of 10.5 moles of sodium hypochlorite. So again, for this, you would have to look up the Ka of hypochlorous acid, and that is 3.0 times 10 to the minus 8. And you can give this problem a try. Pause the video and give this problem a try. Then on the next slide, the solution is provided here. And the answer is 0.62 moles of sodium hypochlorite. And that's the amount you would need to add to 2 liters, enough water to make 2 liters of solution to make the pH 10.5.